In this video, I'll be talking about the Kiwi Drive train, which is a type of holonomic-drive train. Now we're going to talk about holonomic drives. Holonomic drives are true omnidirectional drives, which means that they can move in any direction. A Kiwi Drive is a three-wheeled omnidirectional drive, which means that it can move in any direction with three wheels. The wheels are also 120 degrees away from each other. Here's a simple diagram of what the Kiwi Drive looks like. So I'm going to first talk about forces. Forces have a direction and a magnitude. Forces in the same direction can be added. Forces in opposite directions can be subtracted. And here are two examples. Forces can be broken down into a horizontal and vertical component. If we have a force F at an angle theta, the horizontal component would equal to F cosine theta. The vertical component would equal to F sine theta. For example, if we have a force at an angle of 60 degrees, the horizontal component would equal F of 1/2, and the vertical component would equal F of square root 3 over 2. Now I'm going to talk about torque. Torque is the turning force. For example, a turning force can be used to unscrew a nut. Torque is equal to force times distance. Looking at the diagram, the torque of F around point A is F times d. So how do we make our robot move? We must have forces in the direction of motion. For example, in the diagram, we want our robot to move in a direction parallel to F1, so F1 has to be positive. Forces perpendicular to the moving direction must be 0. So in the diagram, F2 must be 0 for the robot to move in the direction of F1. And finally, the torque must be 0 so that the robot doesn't spin. So how do we make our robot rotate? To do this, our torque has to be greater than 0, and both F1 and F2 have to be 0. Torque will be applied in the direction that the robot rotates. This is a diagram of the Kiwi Drive that shows the angles of the wheels. I use the fact that the angle between each arm of the Kiwi Drive is 120 degrees to then calculate all of the angles. A note is that we are defining the length of each arm as d. We want our Kiwi Drive to move in the y direction. I have named the top wheel to be A, the left wheel to be B, and the right wheel to be C. We are first going to set the force of wheel A to the value of 0. To move it in the y direction, we need to only have forces that go in the y direction. So we are going to turn wheels B and C in opposite directions to have both vertical components point in the y direction. This will result in a net value of F of square root of 3 in the y direction. The horizontal components that point in the x direction cancel out because they point in opposite directions, resulting in a value of 0. The torque will also equal 0 because wheels B and C turn in opposite directions. This is the code to move the robot in the y direction. We want our Kiwi Drive to move in the x direction. This time we are turning wheel A. To make sure the robot doesn't move in the y direction, we are going to spin wheels B and C in the same direction. This will result in the vertical component forces to cancel out and equal 0. However, we have a problem now because the torque doesn't equal 0, since two wheels are moving in the same direction while the other wheel is moving in the opposite direction. In the x direction, if we set F equal to Fa over 2, the torque becomes 0, and the total x direction equals 3Fa over 2. This will allow the robot to move in the x direction. Now we want our Kiwi Drive to rotate. To do this, we want to turn all of our wheels in the same direction. This will result in the forces in the y direction and x direction to cancel out, resulting in only a torque of 3Fd, so the robot will spin in place.